So recall again, now we are calling Dedekind domain as a domain R, which is not a field, and every fractional ideal in this R is invertible. And we want to reconcile this with the previous definition of Dedekind domain. And now we have a theorem. A Dedekind domain is an integral domain R such that R is Noetherian, R is integrally closed, and every non-zero prime ideal is maximal. So we want to prove first necessity, and in this lecture we will prove necessity. So that is, from here we will go here, and in the next lecture we will prove sufficiency. So we will go from here to here. So now we have this definition of Dedekind domain, that is every fractional ideal is invertible, and we will show that these three conditions hold. So first theorem we will prove is, we'll show that if every fractional ideal is invertible in this domain R, then R is Noetherian and every non-zero prime ideal is maximal, and then we will show this condition too. So if R is a Dedekind domain, so that is every fractional ideal is invertible in R, then R is Noetherian and every non-zero prime ideal is maximal. So first we will prove this Noetherian condition. So for Noetherian condition, what we are going to do is that we will pick up some ideal I, and we will end up showing that such an ideal I, any ideal you have picked up in this ring R, this is an R module which is generated by a finite set. So since this is true for any ideal I which I pick up in this Dedekind domain R, therefore R will be Noetherian. So we have to go from picking up an ideal I to this finite set. So since we are in a Dedekind domain and every fractional ideal is invertible, we have I times its inverse is R. So that essentially means you take an element AI in I, BI in the invertible ideal, that inverse of this I, such that this I equals to 1 to m, this AI BI is 1. So you have these elements where I goes from 1 to all the way to m. So this is what this means. So now you pick up any element x in I and you multiply it throughout. So you again copy this summation down. You have multiplied x to the left hand side and x on the right hand side. So this comes here. This we write as xbi ai. Recall that we can do this precisely because we are working in a commutative ring. So you get this. So now this xbi is within R. So this is within R, and that precisely shows that every element x can be now finitely generated by this set, finite set a1 to am, because for any x in I you can write it like this. Now this xbi is in R. This follows precisely from the definition of this this I inverse. So inverse of this module, because this I is an invertible module. So in the definition of I inverse is just elements b in K, which is the field of fractions of R, such that bi lies within R. So this b we are considering as bi, and then we are multiplying it with some x lying in I. So if you multiply x with this b, you will end up lying in R by our definition. And that's precisely why you have xbi lies in R. So therefore this coefficients lie within R. So for every element x, you can generate it rated by a finite set like this. So R is Noetherian, and we always have this finite set because you always have this equation. So instead of x, you can use any other element. So now we prove every prime ideal is maximal. So we will take P, a non-zero prime ideal in ring R, and say it is contained within some maximal ideal Q. So from here we want to go to P equals to Q. So if this non-zero prime ideal is contained within maximal ideal, they have to have equality, and that will show that every prime ideal is maximal. So say P is contained within Q, so then you have this PQ inverse would be contained in QQ inverse, because this P is contained within Q. But Q is lying in our Dedekind domain, and by our definition here, every fractional ideal is invertible. So this QQ inverse would be R. Therefore this now this PQ inverse lies, this is just a product of two ideals, it lies within R. So this is an ideal of R. Now you multiply this PQ inverse with Q, you just get P, which is a prime ideal. So since this is prime, it has to contain either this ideal or this ideal. So either it has to contain Q has to lie within P, or this PQ inverse has to lie within P. So this implication here follows from the fact that P is a prime ideal. Now this possibility that Q lies within P gives P equals to Q, because we started with the fact that P lies within Q. So we are done, and we will show the second possibility does not hold precisely because Q would be equal to R. So now you multiply both sides by inverse of P, and you can do that because every fractional ideal is invertible. So we do that, you get R here. So you copy this, multiply both sides by P inverse, you get Q inverse lies in P inverse P, which is R, and that implies that Q inverse is R and Q is R, precisely because now Q inverse is R, and we have shown that Q inverse lies within R. Now this holds precisely because again we are working in Dedekind domain where every fractional ideal is invertible. So this gives us this. So obviously this condition would not hold because we are saying it's a maximal ideal, not the entire ring. So now we have to prove this second condition. So let X lie in K, which is the field of fractions for our this domain R, and this be integral over R. So for it to be integrally closed, we have to end up showing that this X actually lies within R itself. So we have to go from here to here. So by definition of being integral, so Rx is finitely generated R module, and it has some finite set of generators, say A1, A2 all the way to Am. Now we can always choose an element B in R such that if you multiply B with each of these elements, you land up in R. And such an element you can always choose as, say, the product of denominators of each of these elements. So it clears the denominators essentially. So this is a very important example for understanding fractional ideals. So now by definition, now BRX would lie within R, because you have been able to clear the denominators of all the generators. So this lies within R, and therefore Rx is a fractional ideal. So first thing you notice is that Rx is itself is a ring. So this Rx will give you Rx, and because it's a fractional ideal, this Rx times Rx inverse is R. So now what we are going to show is, we are going to show that this Rx is equal to R, which will imply that X is in R, and we would be done. So this Rx you can write as Rx, because this R is itself contained within Rx. So there is an equality here because R is contained within this Rx. So R is contained within Rx. So this RRX is just this. But now instead of this R, we are going to write this thing. So we copy this thing right here. So instead of R, we write this thing. So now we are using this statement here because Rx is a fractional ideal. So now you can use commutativity because we are assuming all rings are commutative, so we can interchange these two. So you interchange these two. So if you interchange these two, you again get this Rx inverse. We will keep right here, and this Rx, you see this here, you get Rx here. So again you have because of this thing you get R. So we have been able to show that Rx is equal to R, which implies X is in R. So we have been able to prove necessity. In the next lecture we will prove sufficiency.